Okay, so we looked at adding equations together. We add the reactants, we add the products, and we add the enthalpies. That is one thing we're going to keep doing as we move forward in this chapter. The other thing that we're going to do in this chapter is really sort of what we need to be able to do for Wednesday's lab. So we're going to take a really quick look at that, and we may need to lecture for about a half hour before we go to lab on Wednesday. So bring your lecture notes and your lab books and plan to lecture before we go to lab, and that way you'll have all the information you need to do the lab activity. So when we are talking about heat, we talk about heat capacity and specific heat. Heat capacity is an extensive property. Do you remember what that means from chapter 1 definitions? The opposite of being extensive is intensive. Anybody? Extensive means that the property depends on the size of the sample. So heat capacity depends on the size of the sample. And it tells us how much heat it takes to change the temperature of that object 1 degree C. We usually have units of joules per degree C or kilojoules per degree C. You could also have calories per degree C. So if you think about how much heat would it take if I got out my blowtorch and started heating up this bench, we could calculate how much heat it took. But then if I get my chainsaw and saw this bench in half, it would take less heat to heat half the bench, right? So the heat capacity depends on the size. And your author defines it as the heat capacity C times the temperature change delta T is equal to Q. I tend to just write it as words. Heat capacity times temperature change is equal to heat. And this has joules per degree C times degrees C is equal to joules. Now, the important thing is that temperature change is a change. It's not final temperature. It's not initial. It's the change. Delta T is equal to the final temperature minus the initial temperature. So if I'm heating something up, delta T is positive. If I'm cooling something down, delta T is negative. So let's look at the first example. How much heat is required to warm an object with a heat capacity of 25.0 joules per degree C from 2.5 degrees C to 10.0 degrees C? Well, we know our change in temperature, delta T, is equal to T final minus T initial. So my final temperature is 10 degrees C minus my initial temperature, 2.5 degrees C. Gives me my change in temperature, 7.5 degrees Celsius. Now we can use this temperature to calculate the heat. So heat is equal to the heat capacity times the temperature change. So that's equal to 25.0 joules per degree C times 7.5 degrees Celsius. 2 sig figs in my answer, 190 joules. So heat capacity is really straightforward and really simple. But the problem with heat capacity is we can't move it from one situation to another because we're talking about one object. Unless you have that same object, the heat's not the same. So to be able to move between objects and between laboratories, we talk about specific heat. Specific heat is an intensive property, and it is independent of mass. It describes how much heat it takes to change the temperature of 1 gram of substance. So we have joules per gram degree C, or you can think of it as the heat capacity per gram. So we can do the same types of calculations with this one, and we're going to stop here. Bring your lecture notes and your lab books on Wednesday because we will lecture for at least a half hour before we go to lab.